Welcome to our lecture Machine Learning, and in this video we want to talk about classification, specifically linear classification. So as usual, some notation, and important to remember from the last video is that we usually don't include a specific bias offset term W0, but it's usually absorbed, for example, in our data. But here, as usual, our common notation across a different slide deck. Okay. So a quick introduction. So we want to talk about linear classification in this video. And what is the difference to what we have learned so far? The difference is that in the regression, in the last videos, we talked about predictions in the continuous domain. So we have some input features and we predict some numerical values. For example, the house price based on a specific area, for example, or size of the house. And now we want to talk about discrete outcomes like classes, like say object detection. You have an image and you want to say this is a cat, a dog, or a human, for example. So that's the main difference in regression versus classification. So here, just a bit more formally, the setting again. So this is similar to what we had so far also for regression, right? We have our input, data X, often represented as a matrix, n times d as a data matrix. So n different instances, everyone having d features. And then we have a set of possible classes C, 1 up to C, right? Cats, dogs, and humans. And every instance might have a different label based on these potential classes. So every of these Y's, for every sample 1 to n, comes from this set of potential classes. So that's the setup. Here you see an example here. We are measuring like electrodes in a specific muscle, right? We have different features here, the ventral electrode and the dorsal electrode. And then we can measure different states, different classes the muscle is in, right? Like in the rest state, in the co-contraction phase, in the flexion phase, and in the extension phase, for example, based on how the electrodes, what the electrodes measure, okay? And as you know, of course, what we want to do is we want to learn a model based on this. And once we get a new sample, right, so we measure, for example, the ventral electrode shows 1.8 and the dorsal electrode shows 2, then we want to predict this new sample to be, for example, a co-contraction state. Okay, so that's the example of classification, and this is what we want to talk about in the following. And as you should all know by now, is what this means technically is that we want to learn a function. We want to learn a function which now maps from the d-dimensional input, real numbers, to one of the classes. Okay, so it's a set of classes and the output should be one of these. Here it's again written for a specific sample, input xi, output yi. And of course, this might not always match. So what do we have to do for this? So I'd recall quickly the regression setting. Right? In the regression setting, we did 2 steps. In the first one, we had picked a model, right? Which was, for example, a linear model. And in the second step, in the classic view, for example, we picked an error function. And as we learned, this is also like a probabilistic interpretation, but we can pick an error function. So for example, the least squares error function. So these were the 2 steps, picking the model, picking the error function, the loss function. Then we can minimize this loss function with respect to the weights, with respect to the parameters of the model. And then we have a model which well explains our data. So that's a simple 2-stage process, so to say, of what you have to do, picking the model, picking the loss function. So let's start actually here with the second one, which is easier. So now we're in the classification, right? So this least squares loss, where we measure the difference between the predicted and the true value squared, this doesn't really make sense, right? What we can do instead is we can just, for example, use the so-called 0-1 loss, which simply compares the predicted value with respect to the ground truth. And if it's equal, then it's 0 loss. If it's unequal, it's a 1 loss. So here you see our notation. So this here is a predicted value. So predicted class. This is the ground truth class, so the given class. Here we measure whether they are equal or unequal, and this indicator kicks in when the condition is true. So if this is unequal, the indicator says 1, we increase the loss. If this is equal, the indicator 0, we don't increase the loss. Okay. So this is a very famous L01 loss. Ground truth label, predicted values. So this makes sense, right? Because classes are discrete objects, we can't say there's a specific distance between them. So instead of the least squares, we are using this L01 loss. Good. So the second part then is, what is a model? In linear regression, we use this linear function, or if we do a data transformation, arbitrary functions. But it was essentially like the model class was always like linear, was W times double transpose times X. So what do we do here? Indeed, as it turns out, a hyperplane is a very good choice to do this. Why? Let's look at an example. So let's say you have here specific samples from class red, and here you have specific samples from class blue. Of course, it would be a nice idea to separate these two sets of classes by a hyperplane, right? We are separating these classes. On the left-hand side, it's class blue. On the right-hand side, it's class red. So let's focus first of all on a two-class setting to make it not too complicated. So this hyperplane, that's one fundamental core principle used in many, many classifiers or traditional classifier models. So we are trying to find this which separates these. So please note here the difference to regression, and please don't confuse this. So here this would correspond to two input samples, so two-dimensional input, right? So these are two different features. So essentially our data instances are two-dimensional here in this drawing. The classes are indicated by colors. So classes correspond to colors. Classes, meaning label, equals to the color. Okay, so one input feature, two input features, classes are colors. Please don't confuse this with when drawing like a linear regression. So linear regression we have drawn it like this, for example. Here's our x, here's our target, y, and then we have here our function, for example. Right, and here we had our dots around the function. So please note here the strong difference in these drawings. That's very crucial, otherwise you will be confused for the rest of this video. So in linear regression we had input x, output here on the y-axis, and then we had drawn it in such a way, because the output was continuous, we can plot it here on this axis. Here if I draw this means it's a two-dimensional input, right, because we have feature 1, feature 2, and the class label, the y, here these are the y's are indicated by the colors. Okay, so please don't confuse this. But as seen, a hyperplane is a good idea to separate these points. And how do we formalize a hyperplane? A hyperplane is determined by two vectors. On one hand, it's determined by a normal vector, which is orthogonal to the actual plane we are looking at, and then an offset term, which measures the offset from the origin. So please remember that this here now was a two-dimensional space, two-dimensional input space, and then this hyperplane looks like this line if we draw it, and the normal vector is like, as shown here, like a vector which has two components. In general, it might be like higher dimensional spaces, right? Let's say you have a three-dimensional space, like here in the space, then the hyperplane would really be a plane, right? So you see that this is like a plane and not a line anymore. But still, of course, the normal vector is still a vector, as it says, right? Because here's the plane living in this 3D space, but the normal vector is orthogonal to it, but it's still a vector, okay? So this W, here this W, is always a vector, and the vector has the dimensionality as your input space, okay? So here the vector has two dimensions because your input space is two-dimensional. Here we have a three-dimensional space, this is the plane, and the vector has three components, okay? So the normal vector is always a vector, right? And it spans up a plane, okay? So if this is a 10-dimensional vector, so a vector in a 10-dimensional space, then this would be a 10-dimensional hyperplane, okay? So this generalizes to arbitrary input dimensionality. So the dimensionality of this vector corresponds to the input dimensionality, and then plus we have this offset term, which is like the bias term, so to say. Okay, so here it's again written more formally in the small graphic. So we see that the hyperplane is determined by these two factors, the normal vector and the offset. Here you see the drawing in more detail. Here again, orthogonal to it is the normal vector, right? It's perpendicular. And then this bias term is measuring this distance. Be careful, this W0 is not measuring actually this distance, but the distance here is W0 divided by the norm of W itself. Okay, so it's a different scale. Essentially, this is measured in step sizes of the length of W, right? So if you want to look at this from an original point of view, so this length is W normalized by the norm of the normal vector. Okay, just as a tiny detail. And then what we are doing, if we want to use it as a classifier, is the following decision rule. We say if you're on the plane, we might not be able to make any decision, but if you're on one side, it's class 1. If you're on the other side, it's class 2. And why is this easy with a hyperplane? Because the sign of evaluating this function indicates on which side of the hyperplane you are. Meaning if you get a new sample here, for example, right, and you evaluate this, right, you essentially plug in here your blue dot, your two-dimensional vector in this case, right? It's a two-dimensional space. Yeah. It's a two-dimensional space here, right? You plug it in here and you multiply with W and with X, with W0. If it's larger, then you're on one side of the plane. If it's smaller, then you're on the other side of the plane. And if it's equal, you're on the hyperplane. Okay? So this makes this hyperplane approach so simple because you can really just evaluate this and you look whether it's larger or smaller than 0. It's then very similar to let's say to a regression setting where you used essentially this here already as an output, right? You use this as your prediction in a linear regression. And here you're saying if the prediction is positive, so to say, it's class 1. If it's negative, then it's the other class. So that's a nice benefit of this hyperplane view. It's still a very simple decision rule how you make your classification. Still, again, as one side remark, please don't confuse these two different drawings. Okay, so yeah, hyperplanes are very easy to compute, right? It's still a linear function we have to evaluate, and then we get a nice binary classification setting, binary because we have two classes here. Here, one important notion you should all remember. So we call a specific data set, meaning input features X, input instances X, and corresponding targets Y, linear separable if there exists a hyperplane which is able to separate these sets, right? Meaning which says for all X's which are in class 0, they are on one side of the hyperplane, and all X's which are in class 1, they're on the other side of the hyperplane, okay? So it's a statement about the existence. If you can find such a hyperplane, then your data set is linear separable. So this example here is surely linear separable because you can find this hyperplane. On the other hand, for example, if you have like this here, this would not be linear separable because whatever hyperplane you use, this one, this one, this one, this one, whatever, right? You cannot find one hyperplane where red is on one side and blue is on the other side. So this would not be linear separable as a statement, but it's just an existence statement. Okay, good. So now we've established the main idea. We want to use hyperplanes to do classification. And of course, now the question becomes, how can we find these hyperplanes? And one idea is that we use this so-called perceptron. This is one of the, let's say, oldest classification approaches. And the perceptron is more or less just what I explained here. So as a function, as a model, and this is how we started here actually, right? As a model, we use this hyperplane idea. And we are saying if you're on one side of the hyperplane, it's class 1. On the other side of the hyperplane, it's class 0. Okay? So this is our simple perceptron decision rule. It's exactly what I just explained to you from before with this hyperplane. So we are plugging in this linear term and we are applying here the step function. Right, the step function, which is just doing this decision in class 0 or class 1. Okay. So now we have essentially set up both aspects. We have defined the model. We use this perceptron approach, and we have defined our loss function, for example, the 0, 1 loss. So what we have to do now is we have to learn this model. And as you know, right, what this means is we want to minimize our loss function, which, for example, takes the ground truth labels and gets the predicted labels. And we want to minimize it with respect to W and W0. Right? So in this case, it would mean we are minimizing here our loss function could be the 0,1 loss, which sums over all the instances, let's say, and we are checking whether the ground truth label, yi, is unequal to the predicted label, y hat. And what is our y hat? We see it here, right? This was our model function. So we can just plug it in. And f of wt times w transpose times x times w0. And we are optimizing over w and w0. So this would be the step, right? We have the model and we have the loss function overall. And now we want to minimizing this loss, and then we have solved our learning problem, right? So you see that this might not be as easy as before as in linear regression, because you can't just now take the derivative and set it to 0, because you have here this not so nice indicator. The step function is also not super nice to take the gradient off, right? Because here it's not really nice at this 0 point. So it turns out that you can't just do it as simple as in linear regression. So what I will show you in the following is simply the classic result how you can train such a perceptron model. And I will just show you the result, but I won't show you how we can derive it. Because later on in the next week, when we talk about optimization, I will show you a much simpler approach, much simpler compared to the classic derivation, let's say, how you can find this perceptron learning approach. Here I will just show you like the solution, how this looks like. Okay, so how can we learn such a perceptron? So in the first step, we can, for example, just randomly initialize our weights and bias terms. So for example, initializing it with 0. And then we simply follow a very simple update rule. Namely, we do the following. We go through our data. We see which samples are already correctly classified. These we can ignore for a second. But there might be some which are still misclassified. Okay? And for every misclassified sample in our training data, we do the following update. If the sample is misclassified, we see, okay, does it belong to class 1 or class 0? And then we update our weight. And the same, does it belong to class 0 or 1? We update our bias vector. And then we continue. We have new weights and new bias terms, right? And we look at the next sample, which is misclassified. And we update our parameters. We get a new hyperplane, and so on and so forth. So you can intuitively think about it like this here. So let's say you have here again your space. You have your space. You have here samples from, let's say, class 1. Let's call it even then class 1 sample, so to say. Here's your hyperplane so far. And here are class 0 samples, let's say. Okay, so this is your current hyperplane. Okay, and you see now, okay, these are correctly classified, these are correctly classified. This apparently is misclassified. Okay, so we have to follow now this update rule, meaning we have so far, let's say here, this is our current weight vector, our normal vector here, and the bias term we also have, right? But let's focus here on the weight vector, the normal vector. So now we see, okay, this one is misclassified, and we should update this. Okay, this one belongs to class 1. So what do we have to do? We should add the vector itself to the normal vector. Okay, so meaning here, let's say this is the vector of x, right? So this is the x vector. And now we have to update this vector accordingly. Okay, and you see it potentially, right? So let's say this here is our w vector, and this here is our x vector a bit, right? So the w vector might tilt a bit to the other side, right? Because the x here has a smaller slope, so to say. So the new vector might tilt a bit. So for example, it could look like this. Of course, this is now just some hand drawing and might not be exactly correct. But for example, this new weight vector, the new normal vector W prime, which we had here, W prime, has a different tilt, so to say. And we see that now in this drawing, the 1 is now on the correct side. Okay, so one more time, old hyperplane. These are correctly classified. These are correctly classified. We don't have to care about them. Here's one sample X, right? So this is the input X, which is misclassified. It belongs to class 1, as we see. So we have to add this to the normal vector, and then we get a new normal vector. Here's the old normal vector. Here's the new normal vector. So we see that this hyperplane tilts, and then this 1 gets pushed to the correct side, so to say. So the same, we have to update here, of course, a bias term to have the shift, and so on and so forth. And indeed, this approach will eventually converge to some discriminating hyperplane, to a hyperplane which can separate these points, assuming the data set is linear separable, so such that there exists such a hyperplane at least, right? But assuming linear separable data set, we eventually will find corresponding parameters which will do the job, so to say. We can't estimate easily the number, how many iterations we need in advance, but at some point eventually we'll find a solution. So this now might look still like magic to you, right? Why should this approach work where we just tilt and just look at the misclassified samples? But as I said, if you're a bit patient and look the video at optimization, you will see that this indeed is a very, very simplistic algorithm, which every one of you can easily understand after the video of optimization. But so far, just be patient and trust the results, so to say, that this will work to find the correct hyperplane. So you see, at the end of the day, it's very simple, and this classification works then as expected. Okay, so what I talked about now so far was just so-called binary classification, 2 classes, right? We had above and below the hyperplane. And that's all what we can do with a single hyperplane, right? There's no more flexibility, so to say, in what we can do here. But of course, in general, we might have multiple classes. Okay, so let's say we have 3 equal to 3 classes, right? So we have like dogs, cats, and humans we want to classify. So what can we do in this case if we want to use hyperplanes? And there's one idea, or one potential solution, which is so-called one versus rest classifier. What we do is essentially we train classifiers which look at one class and the rest. Okay, so class dog, where there's a rest. Class cat, where there's a rest, right? And then it looks like this here a bit. So let's say we have these 3 classes. We'll train one classifier C1, C2, where there's a rest. So not C2, so to say. So class 1 and class 3. We train one classifier C1 and not C1. And here actually we might not need to train another classifier, because if something is not C1 and not C2, it should be hopefully class 3, right? Because we have 3 classes. So this looks like a nice idea at the moment, right? But indeed, it's not really super convincing, because what is with this regime, right? So here it's class 1. Okay, fair enough. Here it's class 2. Fair enough. Here it's not class 1 and class 2. So it's class 3 apparently. But what is here? Actually, this should be at the same time class 2, right? Because it's on this side of the plane, right? In this regime. But it should also be class 1 because it's this side of the regime. So what do we do with this green region? Is it class 1 and 2 at the same time? It's a bit unclear, right? So what can we do? So one versus rest is one solution, but not potentially not the best one. So we can also do 1 versus 1, which just blows up the space, so to say. So we're always comparing class 1, class I versus class J. So in this 3 class case, it means 1 versus 2, 1 versus 3, and 2 versus 3, right? So this is what you see here. 1 versus 2, 1 versus 3, and 2 versus 3, right? So by the way, what this means is the following, right? So we take only the training data from class 1 and we take only the training data from class 3. And here it means we take only the training data from class 1, and here we relabel the remaining training data as not class 1, right? Just to be very specific. So what does it mean here, right? So we do these now 3 different hyperplanes. This is still not very perfect, right? Because here in this regime, we might have C1, or even actually in this regime, we might have class 1. Right? In this regime, we might have class 3. And in this regime, we might have class 2. Right? You see where these classes are pointing at. But what is here in the middle? Right? This is neither C1 nor 3 to class 3 nor class 2, right? So we have here something like an empty regions, where here two classes at the same time occur, here no class at all occurs. So also does not seem to be the optimal solution. So what we then do often, in many different versions at least, in many modern classifiers, is that we do a so-called multi-class discriminant. What this simply means is, and we don't just train, like here, this kind of 3 hyperplanes, but actually we do train 3 functions, but not 3 hyperplanes, but we train these kind of linear functions we have seen before, right? We have seen before that we had a hyperplane was essentially determined by this normal vector and the bias term, and now we don't really span the full hyperplane, but what we are saying is just we train 3 of these functions for every of our classes, and then we just take the argmax. A bit of what you see in a probabilistic point of view, take the maximum probability. So here you just take the class which has the largest term here. Okay? And then how it will look like, this kind of Voronoi cells. You get a region which is class I, or class 1, class 2, and class 3, but you don't have these empty regions. Okay? So you assign the x to the class where you obtain the highest score in this function. Similar a bit to like a probabilistic interpretation, but just now, of course, this is not a probabilistic value. As it turns out, this still leads to like linear decision boundaries. We talked about decision boundaries in the K and N. Decision boundaries are the boundaries between different classes where we technically can't make any decision, right? So this here is either I or J, this is I or K. Here we even have 3 classes meeting. So here we are, so to say, undecided. And then this multi-class discriminant, we get here like these linear decision boundaries. Okay. Why is this the case? That's very easy to show, right? Because every class is represented by these linear functions. And these lines correspond to those cases where 2 functions match, right? Where we have, for example, here in this case, on this line, we have that function I, so it's class I here in the general sense, equals to the function of class K. Right, so on this line, the prediction for both classes is the same, right? The outcome of both classes here is the same. And since this is a linear function, and we set it equal, then of course here the solution to this equation is of course also like a linear term. Same here, and overall we get this nice linear separation between the classes. Okay, so this multi-class discriminant, this is what you should usually use if you have multiple classes. Just learn multiple of these and take the argmax. Okay, so we can handle now multiple classes. That's easy by doing this kind of multi-class, multi-discriminant setting. What about non-linear separable classes? So similar to linear regression where we had like linear dependencies and non-linear dependencies. Of course, here we can ask, what if we have linear separable data? Sure, use hyperplanes. What if you don't have linear separable data, meaning non-linearly separable data? Like this here, for example, right? So here we have like, again, a 2-dimensional space, colors indicate classes, but here it's not linear separable. Whatever hyperplane you pick, right, you can't separate blue from red. So what can we do? And this is very straightforward, I guess. We can again apply our trick of basis functions, of transforming the raw data to some other space, extracting features, so to say, right? So we're again looking for a function which maps the original d-dimensional data to some other m-dimensional space. And here in this simple example, you can see what we can do. We can, for example, extract 2 features. On one end, we can extract the angle. So like here, what is the angle this feature has, right? So this is a small angle, this is a larger angle, and so on and so forth. Or we could also, for example, look at the distance from the origin, right? So this is close to the origin, this is far away from the origin, this is also far away. And then we can plot it into a new space. Okay, so here, for example, you see the angle, right? Oh, sorry, here you see the angle, and here you see the distance from the origin. And then you see, okay, now we can linear separate it, right? So as you also see here, not both of these features are actually important, right? It would be enough to use this feature, right, the distance from the origin, because then we can already separate red from the blue side. but we could of course just extract more features and a priori potentially don't know what features are relevant. Again, it's a question of, for example, model selection. But here in the 2D space, you clearly see that we can find a linear separable hyperplane. A hyperplane which separates it linearly. Okay, so this idea is extremely straightforward, right? We can use basis transformations. We will see this later on also in the chapter of support vector machines, where we introduce the notion of kernels, which are essentially also by basis function, which has specific properties, and then something nice follows. And you will also see it in deep learning already, like as a spoiler. In deep learning, we more or less have trainable basis function. We automatically learn what are the best features we should extract from our raw data, because that's the core idea of deep learning. We start with the raw data and then we hope that the neural network itself extracts the relevant features. But at the end of the day, it all boils down to transforming your raw data to some other space where life is easier, so to say. Okay, so we have seen multiple classes. We have seen that we have this linear case and this nonlinear case, but there is some problem still here present, which is due to the fact that we learned here so-called hard decision boundary or hard classifier. Hard means really in the sense that we have this hard boundary and we say on this side it's red and on this side it's blue, as you see it in this plot. What is the drawback? The drawback is, for example, as shown here, that in some cases we might not be able to separate our data, even not after transforming it, because you see that here the classes are somehow like overlapping, merging together. So here we have this kind of noisy behavior, and the linear separation hyperplane won't be able to succeed here, right? So we won't be able to find a hyperplane which correctly classifies all these samples. And this is a big problem of hard decision-based classifiers. So we can't handle this noisy data. Of course, we also don't get a nice measure of uncertainty. This is also what we have already seen in the regression setting. The optimization point of view, the classic point of view, doesn't help us with uncertainty, but we might want to have uncertainty to get a better feeling about our predictions. And then finally, these approaches I have shown you, specifically the perceptron, often leads to rather poor generalization, and it's also rather difficult to optimize. I've shown you this solution, which looks easy, but inherently these hard decision-based classifiers might be hard to optimize, specifically if you look at the 0-1 loss, which have this kind of step function where we have very hard learning. Also, if you look later on at gradient-based learning, which is very hard to do for such hard models. So what are the alternatives? So what if we want to not use hard decision-based classifiers? I guess you can already guess the solution. We want to go to some probabilistic world. Probabilistic classifiers which take like uncertainty into account, which give you some notion of likelihood how your prediction behaves, for example. And this is what we want to discuss in the rest of the videos. But before we start on that, let's first take a short break.